All right, canonical ensemble. We start with a small EI, which is just your deviation in a large reservoir. So this will be labeled EI. This will be your reservoir energy. This is, if we talk about it as a particle, which is not what is transferring, it is energy, but it's easier to view it in terms of energy or particles first. This is your tons of particles, and this is your single particle. Now I'm going to draw a box for E total of the whole system, which would just be the submarine shape. I'll make it a little bit bigger and call that E total for visualization. Now this is isolated from the universe, so there's nothing else in existence. It's the energy that is just there, composite of everything forever and ever. And that's where entropy starts to form. This is the equation for entropy. KB is your Boltzmann constant. It's used to change temperature units to joule units. And W is your measure of microstates for an accessible macrostate. So the whole ensemble, all the probabilities, what macrostates arrive, and the numbering of measuring how many of those there are, possibilities. And so to explain that, in the whole system, if it was a room with particles, one particle in a corner, all the others in another corner. That's one microstate. Half the particles here, half of them right there, that'd be another microstate. All of them evenly distributed, that'd be a microstate. All of them in a spiral fashion, that'd be another microstate. Two of them over here, 50 over here, the millions of others right there, that'd be another microstate. And your ensemble is measuring the probability of how many of those from the deviation of EI out of the whole total energy system arise. And the probability of this influencing the macrostate that becomes accessible. So that's really defining entropy, and we're not looking at particles and location where one's here and here, we're looking at energy transfer. And the whole system is right here. So how much energy is going to EI, how much to ER. And there's none in and out of the system, it's isolated. This is it. So we'll take E total is equal to EI plus ER. So the reservoir plus the EI, your deviation, goes to the total. Now we want it in terms of probability. So we'll have probability is equal to 1, the whole. 1/2 of how many of the whole out of 1/2. The whole is what your probability is. It could be out of 50, 25 out of 50, the whole would still be 1. So we want that proportional to the number of macrostates, or the measure of accessible microstates per macrostate. So if we move EI from the E total, so the total and this one deviation is right there, that'd be proportional to, we'll label it omega R of E total minus EI. And this is the number of microstates of the reservoir. Now we'll plug this into this equation, and we'll have S of E total minus EI is equal to KB log omega R E total minus EI. Now we want to get this in terms of omega R, so we can plug it in equal to P. So we'll divide by KB, so that goes over there, and natural log is base E, so we'll raise to the E to the exponent. So it'll be omega R E total minus EI is equal to E raised to the S, it's really SR, of E total minus EI over KB. Okay, so now we're going to take this tiny portion and think about it for a second. EI and E total. So the total number of what macrostate is actually there based on the total number of possible microstates. There are so many possibilities. There are millions and millions of configurations, and EI is a really small deviation. If it was just one energy unit or one particle, it's really doesn't have that much influence in comparison to all the other possibilities. So we're going to think of it as when you do a difference quotient for your slope in calculus, you're trying to narrow in on the smallest limit and deviation from a single point possible on both sides to get to the behavior that's changing. There's some philosophy arguments against that development in calculus, but we'll do something similar, and it's f of x plus delta x. It's not a difference quotient, but EI will be delta x, E total will be x. And we'll do what's called a Taylor expansion. And so that gives you f of x plus delta x over 2 f prime of x plus, actually it's not over 2. The next one is delta x squared over 2 f double prime of x, and so on. And then we'll plug these E total and EI into that just for this piece of the equation. And I'll say right now, so we don't have to write it, the higher order ones, it goes on to 3 and 4, etc., etc. Those will be eliminated. EI is so small, and they will be very small. They'll be negligible for probabilities compared to the whole. So write this out, and we'll have SR of f of x, SR of E total is f of x plus negative EI. F prime of x will be partial s over partial E. And now we write that back into there. And so we'll have, and omega r, since it's right there, is also equal to P. Well, it's actually proportional to P. So now we'll have proportional to this is E raised to this, SR, E total. And we can split them right there since they're both in the exponent. And it'll be E raised to the negative EI. This is over KB minus EI to the partial S over partial E over KB. Okay, now the thermodynamic relation, partial S over partial E, is at constant volume and constant number of particles is equal to 1 over T. So we can plug that in for that one. Now this piece concerning the E total, we're looking at the probability of this single microstate affecting the macro state. So if E total is always the same, regardless of where EI is, could be located, even though it's not a particle, or condition, whatever condition EI is, the total number of possible is always going to be the same. So this would be considered a constant. We could just write this as a constant A. And because it's a probability, A is not going to influence the probability at all. It would just scale the entire thing, similar to 1/2 and 25 out of 1, or 50 out of 100, or 25 out of 50. They could all be multiplied by A and there would be the same thing. So we can eliminate this because the total will be constant for every possible. So then we have probability proportional to E to the negative EI, and we plug in 1 over T over KB. And that's going to be written as negative EI over TKB. Probably is proportional to that. Now we can define beta to equal 1 over TKB and plug beta in. So we have probability proportional to E to the negative EI times beta. Now our partition function, Z, is the summation of E to the negative EI beta, which we have right here. And our probability summation, we want equal to 1. So we're going to want to use a clever form of 1, which will involve bringing the total back in. So this is for a single microstate, EI. What's the probability? Okay, that could be, doesn't really tell us anything other than with regards to some number. So we need it not to be proportional, it still be proportional to the probability of it actually arising, it would have to be out of the whole. So if we divide by the summation of all those possibilities, for every microstate, single one, the summation of all the possible ones would be the same as E total, or E total. And so we can write it as e to the negative ei beta over zeta z. So this is all the possible microstates again, but summation. And this is a single one, and that's your probability. And this is the canonical ensemble, or the statistical chances that entropy continues to increase, that this microstate is going to arise as the macrostate that develops with regard to all the so many possibles for the reservoir, a single deviation.